Okay, so we want to talk about contingency tables today. So the first thing I want to talk about is what is a contingency table. So when we look at the topic at hand here, we want to think about this idea of what type of variables that we've already studied. So a contingency table is actually the distribution of two qualitative variables at the same time. So as you can see, if you look down at the example below on the bottom of the page, you can actually see that we've asked these students two questions. If you just glance down, do they have a sore throat or no? Do they have a runny nose or no? So we asked two yes or no questions, and yes or no is qualitative data. We actually gather the answers to both questions at the same time, and then we display the data as seen below. So the idea here is that we use this table to explore probability concepts because there's a ton of probability questions we can answer here. But we also use this table to explore the idea of independence. So these are all ideas that actually come straight out of chapter 5. So you can find some contingency tables in your online homework from chapter 5. But most importantly, we want to use them to focus on understanding probability at first, like how could we use this table to understand probability? And then when that's complete, we want to focus on how we could use that same table to understand independence based on what we've already constructed. So let's just take a look at the example that we've got, and we'll work through these questions so you can see how we would use a table like this to assess a question about probability. And from there, you should feel a lot more confident for your online homework. Okay, there are 25 students in a sixth grade class on a cold winter day in February. Many of the students had runny noses and sore throats. After examining each student, the school nurse constructed the following table. Answer the questions based on the information provided by the school nurse. Okay, so the very first thing I actually want to do is find the totals of each of the categories within this table. So the first thing we're going to do is add up each of the columns in each of the rows. And I do think for some reason, maybe it's because many, many years of adding vertically, that it's just easier for me to add the columns first. And then I'm going to go across and add each of the rows. So how many total students had runny noses? That's 18. And that did not have a runny nose, that's 7. And then finally, in this bottom right corner, I want to check that the sum is in fact the 25 students that have been seen in the sixth grade class above. So we can see that both 10 and 15 add up to 25 and 18 and 7 will add up to 25. So that 25 as our total in the denominator, that's actually going to be the total. This will be the denominator used for all probability questions unless a condition is applied. So if you go back and think about chapter 5, the conditional probability formula has the word given in it. So when we apply, that's just the basic way of writing that formula. So when we apply a condition, we actually are going to see that word given, and we will see the denominator shift to being a smaller number overall for the final answer. Because when we say given someone has a runny nose, then we actually are only looking at the students who have a runny nose. We're excluding all the students who do not. So that's important to think about how our denominator is constructed. Okay, so let's answer these questions that we see below. What is the probability a randomly selected student had a runny nose? So as we can see, only one of the variables was mentioned, just having a runny nose. So I'm going to go ahead and use RN for runny nose. To find this answer, what we want to do is think about what our denominator would be and what our numerator would be. So our denominator should be all 25 students because we have not been presented a condition here. Our numerator should be all the students who have a runny nose from this chart. So to find that, we'd actually have to go out to our column that we created, that is the total, and find the total students who had that runny nose on that specific day And if we simplify that, because Alex will typically ask you to simplify that, we would get down to a 0.72. Let's try the same idea one more time. What is the probability a randomly selected student had a sore throat? So this time the student has a sore throat. They do not mention anything about the status of the student's nose. So we have no idea what's going on with their nose. So let's go ahead and stick our 25 on the bottom. We do know our denominator has to be everybody, and find all the students who have a sore throat. So I'm going to give you a second to look at the picture. I want to find the total number with a sore throat, and that is 10 students. If you got that right, congratulations. And if we simplify that, we get down to 0.4. Sorry if you can hear my dogs barking outside. All right, just a couple more questions to go. What is the probability a randomly selected student had a runny nose and a sore throat? Okay, there's one of our keywords. So let's go ahead and use this pink pencil. The word "and" is actually going to be at the intersection of a row and column. So in this table, the word "and" actually means that we answered both questions at the same time. So that would be somewhere inside the table. So I'm going to go ahead and try to find that number, and I'm going to highlight it inside the table. So it says runny nose and a sore throat. So they actually said yes to both things. So that means they said yes to having a runny nose. I'm highlighting that in the table. And they said yes to having a sore throat. That is this number of 6 students right there. So we want to use that 6 to write our final answer. This is a student who has a runny nose and I'm going to use the word a sore throat. So that was 6 students out of the 25 total students that we had surveyed at the beginning of the day. If I simplify that, I get 0.24, 24 hundredths. Okay, so that's the word "and." That's one of our ideas from chapter 5. So let's take a look at another idea from chapter 5 appearing right here. What is the probability a randomly selected student had a runny nose or a sore throat? Okay, so this is the word "or," which is our addition rule. So what I'm going to do is write the rule right above in its standard form. That would be A or B is the probability of A plus the probability of B minus the probability of A and B. We want to use that rule to be able to take into account the fact that we may or may not have counted people twice here. And in this case, we definitely have people who we may have counted twice when we look at the outside numbers. So let's take a look at what I mean. Let's use our actual letters. These are students who had a runny nose or a sore throat. So we would find the probability they had a runny nose plus the probability they have a sore throat. I'm just using our variables instead of A and B. And then we're going to subtract the probability they had a runny nose and a sore throat. So we want to make sure we're doing this correctly. I still do not see the word "given," so everything here is over 25. So this is over 25 plus something over 25 minus something over 25. And I know it might have been a really long time since we've dealt with fractions, but that does mean that the final answer is also over 25. So let's focus on the numerators. How many students have runny noses, right? So we had 18 total students that had a runny nose, 10 total students who said they had a sore throat. And I want to go up to the picture just quickly and illustrate something for you. Just take a look at what I'm about to show you. We've got all the students that are 18 that had a runny nose. We've got those 10 students who had a sore throat. And if you saw me highlight through both of the column and row, I just highlighted the 6 students who have a runny nose and a sore throat twice. Okay, I literally just counted them twice. And that's not okay. They're only appearing in this table one time. So I do have to go down here to my formula and subtract 6 over 25 students. So let's do this math. What's 18 plus 10 minus 6? So 18 plus 10 is 28. 28 minus 6 gives me 22. And if I stick that into the calculator, To simplify it, I get a 0.88. Great job. Only 2 more questions to go. Keep up with me, guys. We're almost done. Ooh, look at this keyword. Given a randomly selected student has a sore throat, what is the probability they also had a runny nose? Okay, that is one of our keywords as well. So we're going to want to make sure we're clear on this. First, it says given they have a sore throat. Then it says, what is the probability they have a runny nose? So first of all, I want to write out our general formula using the letters A and B, and then we'll substitute in with the letters that represent something from our table. Our formula, if I can get my pen to work, looks like this. The probability of B given A is equal to the probability of A and B. So both things are happening in the numerator. But in the denominator, we're dividing by the probability of the condition, which is the thing that already happened. So for us, that comes after the word given. So remember, this reads B given A. So let's go ahead and be careful. When we set this up, I always actually write the given line and then whatever comes after it first. So look back up at the problem. It says given the student has a sore throat. So first, we write down the given statement. They had a sore throat. Now, among all of those students, how many also had a runny nose? So now if we read it out, runny nose given sore throat. And that's exactly what this question asks, because they mention the sore throat right after the word given. Let's set it up. Our numerator should be students who have a runny nose and a sore throat, while our denominator should be the students who have a sore throat. That's our condition. Whatever comes after that word given. Okay, this is a little weird because it's a fraction within a fraction, but I'm going to remind you of one more thing that we can do to help our lives get easier. Runny nose and sore throat, the probability of that is 6 out of 25. Now in the denominator, the probability someone has a sore throat, well, that's just part B. That's 10 out of 25. But this is really complicated looking. It's a fraction within a fraction. So if you remember, a fraction divided by a fraction is actually the same as multiplying by its reciprocal. So if we multiply by 25 over 10 instead of dividing by 10 over 25, then we see that this, in fact, is 6 out of 10, or I'm going to try to fit that. My goodness, my handwriting is too big, which reduces to 0.6. And let me point out that this, I'm going to put a star next to this 6 over 10, and then put a star next to this comment at the top of the video. Notice that that 6 over 10 reflects the comment we made all the way at the beginning. The denominator 25 is going to be used unless the problem says the word given. So this is where you see our denominator has shrunk because it says the word given and we've applied a condition. One more question, we're almost there. Based on the class's data, are having a sore throat and having a runny nose independent events? Okay, we're going to go back to an original rule back in chapter 5. The rule from chapter 5 said A and B are independent events if the probability of B given A is equivalent to the probability of B. So what this means is that A has no impact on B. Okay? If the probability of B given A is simply equal to the probability of B, then it does not matter if event A already happened or is a condition to this probability. So let's check if we can find two numbers that are equal. If these two probabilities are equal, then we can say the events are independent. Now, I prefer to use something that's already been done. So I look above at the previous given statement. Just above in part E, we showed what it is to have a runny nose given a sore throat. So we know the answer to that. Now let's see what we would have to show that that's equal to. So that's a question mark. Are these two things equal? Okay, so take a look. I replaced event B with having a runny nose, and I replaced A with a sore throat. So we want to test whether or not this is the same as the probability that the student has a runny nose. If these two are the same, then having a sore throat has no impact on the runny nose itself. Okay, now, as a trick, I said we were going to use something we'd already written. So this right here is part E, and if you actually look up above, this other side is part A. So we know the numbers that we need to substitute on either side of this equation. So on the left side, I'm going to substitute the answer I got in part E, which was 6 out of 10. And I want to know, is that the same as the answer we got in part A, which was 18 out of 25? Comparing fractions is hard, so let's go ahead and compare the decimals. On the left side, we have 0.6, and on the right side, we have 0.72. These numbers are, in fact, not equal to one another. So I'm going to put a not equal to symbol between them. And because they are not equal, this means that these two events are not independent. The only time we can consider the two events to be independent using this rule is if the left and right side of that equation or that statement are the same value. If you see the same value on the right and left side, then we can say, yes, the events are independent from one another. Great job keeping up with me. I know that was a long video.